So what is squeeze theorem? Sometimes called sandwich theorem. No, I'm not making this name up. I know that I love food, and yes, calling something sandwich theorem sounds something like Chavez would say. But even though I love food, I did not make that name up. So here's how the squeeze theorem works, guys. If I were to say prove that the limit as x approaches infinity of, I'm going to choose cosine x. Cosine x over x equals 0. So if I want to prove that, here's one way to do it. And this is called the squeeze theorem or sandwich theorem. I'm going to say cosine x, and I'm going to say less than equal to, and then greater than equal to, and I'm going to put that in the middle. Cosine x oscillates between -1 and 1. So what I'm going to do, I'm going to focus on these ends, guys. And what I'm going to do that is because, look, this is cosine x over x. So I'm going to go divide by x. Whatever you do to 1, you got to do to all of them because there's an equal sign there. Divide by x, divide by x. I'm going to find the limit of this guy here on the right. Limit as x approaches infinity of 1 over x. And I'm going to find the limit of this one here on the left. Limit as x approaches infinity of -1 over x. Well, as x approaches infinity for 1 over x, 1 divided by a huge number, like delta math says, delta math says 1 divided by big. So 1 divided by something big is going to be 0. Coming back to this one, the one on the left, -1 divided by something big is still 0. So by the squeeze theorem, and I can state that, so by squeeze theorem, comma, since the limit on the right-hand side was 0, since the limit on the left-hand side was 0, look, cosine x over x is sandwiched. So by squeeze theorem, limit as x approaches infinity of cosine x over x must be 0. Happy face. Oh, that happy face came out a little weird. That's okay. Weird is okay sometimes. How do we feel, guys? Did that make sense to you guys?
Yes.
Okay.
Yes.
Awesome. I'm happy that it made sense. All right, guys. Now we're going to talk about what it means to be continuity. So this is coming from some textbook. I don't remember which one. Probably the Demana. And it says interior point, a function y equals f of x is continuous at an interior point C if its domain, blah, blah, blah. And then the endpoint, a function y equals f of x is continuous at a left endpoint A or is continuous at a right endpoint B if its domain, blah, blah, blah. Okay, what does that mean? Let me tell you what this one means. I'm going to write this one in red. That one means that the limit from the left equals the limit from the right, which equals the value. So limit as x approaches C from the left of this function equals limit as x approaches C from the right of this function. And of course, so right there, that's the definition of your limit existing. So if you approach the limit from the left, if you approach the value C from the left and you approach the value C from the right, and all that equals f of C, you are continuous. You are continuous. Chavez, what does that mean? Can you tell me in plain English? Yes, it means this. So the way I have it right here, see, right now, at the moment, the limit exists. As soon as I cover that hole and make it solid, it's continuous. Because not only does the limit also equals f of C. F of C just means some y value. That just means your value. Your y value. And I don't really want to put quotes on it, guys, because quotes kind of means like, is it really? But in this case, it literally means whatever your f of x is or your function is. Now, what does this mean in blue? It just means at an endpoint, guys. So if I have something like this, I'm going to call that C, and I'm just going to say like I have a square root function. See? So there's only one direction you can come at. The only time that you can go to that endpoint is from the right-hand side. So limit as x approaches C from the right-hand side of f of x equals f of C. And now what about if I go from the left-hand side? Okay, let me do the left. Oh, let me change colors so I can write. If I have a C right here, there's only one direction to approach C on this one. So limit as x approaches c from the left-hand side, because that's the only direction I can come from that, is f of c. See, so there it is, guys, color-coded and everything. Hopefully I'm doing a good job here of writing notes. I would appreciate a thumbs up when these notes go live, if you guys feel like being generous. All right. There are 4 forms of discontinuity. I think you asked this question once, Tiff. I think you asked like something was oscillating big time at 0, and you asked like, what is this called? It said it does not exist, and I think this is one of them. So there are 4 forms of discontinuity. Three of them are very common, 1 not so much. And actually, I shouldn't have even said that, 1 not so much, because it is common, but there's not much you can say from it. So I don't see professors or teachers asking much about it. It's this one. See, this one just keeps isolating, going back and forth, back and forth, back and forth. And you approach 0. Well, at 0, you're undefined. It just keeps going. So what happens? This is called discontinuity. It's called the oscillating discontinuity. Because it just keeps going back and forth. Oscillating discontinuity. And that's all you can say about it. Like, there's not really much you can say about it. So it's not very exciting. So here are the ones that are exciting. So here are the 3 that are exciting. So the most common one are these. So you have something like this. You're defined it for all real numbers, and you don't have to be defined. And they call this gap, you see that gap? They call that a jump discontinuity. And I'm just gonna put DISC. Discontinuity, I can't spell it all. There it is, discontinuity, whatever that word is. It means not continuous, obviously, right? All right, what is the other way? What is the other form of discontinuity that's very common? The other form of discontinuity is when you have like vertical asymptotes and goes like this. See, it's discontinuous because you can't, there's no way that you can draw this graph without lifting the pencil up from the graph or from the paper. So this type of discontinuity, there's a word for it, it's called infinite discontinuity. Infinite discontinuity. And then there's one more. And one more. I'm remembering of a YouTube video. You guys probably don't remember what I'm talking about. Anyways, let's continue. This is the last one. This, it's a hole, but what they call it, it's a hole, but the mathematical term is removable discontinuity. Removable discontinuity. Why did I spell this one and not the others? I don't know, guys. I was just writing some stuff down, and for whatever reason, it just felt right to write it all out. I know maybe I'm getting you guys mad because I'm not consistent with how I write here. It just depends, guys. That's how life is. Sometimes it's just random. So don't get mad. All right, here we go. Only one of these 3 can be made continuous. So write that down somewhere. Only one of these 3 can be made continuous. Take a guess. Which is the only one that could be made continuous?
The removable?
Yeah, that's the only one. Good job, Mazuka. That's the only one that can be made continuous, guys. If I tell you that I plug in, if I go f of c equals 5, and here's 5, and this is c, all of a sudden, OMG, it's continuous. Do you guys see that? So the only one that could be made the only one that could be made continuous is the removable discontinuity. That's it. You cannot make the jump continuous because then you would be connecting a vertical line, which a vertical line, remember, is no longer a function if you do that. And you cannot make the vertical asymptotes continuous because you can't cross vertical lines, guys. All right, let's keep going. Hopefully you wrote that down somewhere, that the removable discontinuities are the only ones that can be made continuous if you wanted to. Find where the graph is discontinuous, identify the type of discontinuity. Okay, so endpoint, good, endpoint, good. All right, I'm good, guys. The only type, let's see, boom. What happens at x equals 1? By the way, it could have been a hole in a hole. It doesn't have to have, it doesn't have to be solid at one of them. As long as you see a gap, you're good. What type of discontinuity is that, guys?
Jump.
Yeah, it's a jump. And don't just say jump, say jump discontinuity. Jump DISC. All right, I see a hole there. Don't call it a hole. Well, I gotta be careful with how I say that word, right? Anyways, I probably should be, let's just continue. Don't call it that, call it something else. It starts with the letter R. What am I gonna call it?
Removable discontinuity.
Yeah, removable discontinuity. And that's it. Those are the only two discontinuities I have in this one. And by the way, they didn't have to put a point up there. They did. So my domain is all real numbers in this case, because I'm defined, well, okay. My domain is from -1 to 3, sorry. You're defined for every x value, but they didn't have to put a point up there. All right, let's go to the next example, guys.
Wait, Charles.
Oh, what's up?
Why wouldn't, like, for the 2, why wouldn't that also be a jump?
Oh, because I don't have, okay, there is a gap, but this is not part of the curve. This is just a point. It's just a singularity. You have to have, see, like this is a curve and then a curve. It needs to be two curves, like a curve, then a gap, and then another curve. It can't be a point, a singularity like that. Did I answer your question?
Yes, thank you.
All right, example 2. Consider the function g of x. So I have a piecewise function, I have a parabola, a linear line, and another linear line. And they tell me the domains. What two limits must be equal for g of x to be continuous at x equals -2? Oh, that's simple. They're just asking for limits. So what two limits? This is coming from the left. So the limit from the left must equal the limit from the right. So I'm going to write limit as x approaches 2 from the left. And now I could write g of x, guys, but I'm going to go ahead and write this expression of kx squared plus m, because that's the expression for the left. That better equal the limit as x approaches 2 from the right. And from the right, it's the 4x plus 1, of 4x plus 1. Did everyone understand that, guys?
Yes.
Okay, because they have to have the same y value. So there it is. Do they want me to solve? It doesn't look like it. It just looks, they just said to get my two limits, and there's my two limits. All right.
Wait, Charles.
Huh?
The limits, we're approaching -2, right?
Yes, man. Good catch. Plus a point. Man, from the left-hand side, -2 from the right-hand side. I can't believe I made that mistake. Grr. Grr. Boom. Okay, anyways. What's the next one? What two limits must be equal for g of x to be continuous at x equals 3? All right, again, the two limits, this one's going to be from the left, and then this one's going to be from the right, with respect to 3. So limit as x approaches 3 from the left of 4x plus 1 better equal limit as x approaches 3 from the right of kx minus m. All right, I think we're done. Okay, no, now they want me to solve for m and k. Determine the values of m and k so that the function is continuous everywhere. Of course, right? We can't just have it that simple. All right, the magic here is on the middle one. So let's figure out what this side is, because there's an x value there. So I can plug in 4 times -2 is, okay, I guess let's do it right. So here's m. M's in red. Limit as x approaches -2 from the left of kx squared plus m, kx squared plus m equals limit as x approaches -2 from the right of 4x plus 1. This right here, 4 times -2 is -8 plus 1 is -7. So limit as x approaches -2 from the left of kx squared plus m, oh, I'm going to have a system, by the way, equals -7. If I plug in a -2 in there, guys, -2 squared, so here it is. I'm no longer going to put the equal sign. I'm no longer going to put the word limit. So -2 squared is 4, so 4k plus m equals -7. So I'm going to have a system. Write out a system of equations. All right, I'm going to do the other one over here in blue. Limit as x approaches 3 from the left of, I have it right here, 4x plus 1 equals limit as x approaches 3 from the right of kx minus m. All right, here we go. 4 times negative 3 is negative 12, plus 1 is negative, oh, it's a positive 3, sorry. 4 times 3 is 12, 12 plus 1 is 13. So 13 equals, and I'm just gonna plug in a 3 in there, guys, 3k minus m. All right, here's what I see. M equals 3k minus 13. I'm gonna substitute this expression in right there. 4k plus, and what is m? 3k minus 13 equals negative 7. 4k plus 3k, 4, 5, 6, 7, 7k. And I'm going to move the 13 to the other side. Equals the difference between 7 and 13, 7, 8, 9, 10, 11, 12, 13. 6, negative. Oh, no, positive. 13 is larger than 7. Divide by 7. K equals 6/7. There's my K value. Now I got to find my M. Plug in that K value right there. M equals 3 times 6/7. Let me know if I made a mistake, guys. Minus 13. M equals 6 times 3, 6, 12, 18. 18 over 7 minus 13. Multiply that 13 by 7. I don't know what that is. Let's see, 77 and 14, 77, 87, 97, 89, 90, 91, 91. So this is 91 over 7. So M equals 91, that's a negative, 91, 81, 71, 73. Negative 73 over 7. If I made a mistake, let me know. But there they are, guys.
Two equations for the first one. I know we did kx squared plus m equals negative 7, and then we did 4k plus m equals negative 7.
Yeah. Because negative 2 squared is 4, right?
Oh, okay, yes, I see what we did.
I plugged in a negative 2 in for x.
Okay.
I don't see any mistakes, guys. If you want to check, which I don't know, maybe we should check. So let's see, what was my first equation? So g of x looks like, let's see, we're right. What did we say k was? 6/7? All right. So 6/7 x squared, and then m was negative 73 over 7. Plus a negative, so minus 73 over 7. And then 4x plus 1. And all I'm going to do is just take those two, see if they work. And let's see. So at negative 2, I better have these match. So let's see, 6/7 times negative 2 squared minus 73 over 7. That better equal 4 times negative 2 is negative 8, plus 1 is negative 7. That better equal negative 7. Let's see if it's true. 2 squared is 4. 4 times 6, I believe that's 24. 24 minus 73. Let's see. So 73, 63, 53, 49. Yep, it works. Negative 49 over 7. Does that equal negative 7? It does. Yep, it works, guys. So it worked for these two. You guys should check out the next two if you guys want. It will work because we got the M from the other one. So there it is, guys. That's how we do it. How do we feel?
Good.
Okay, let's keep going. Is this the last one? Okay, almost. We're almost there, guys. Example 3. This is coming from UH. Sorry, UH quiz is coming soon. Actually, UH quiz is coming now. Sorry, guys. I'm having too much fun here. Given that this function, define the function f of x at x equals 5 so that it becomes continuous. Okay. What did we say earlier about the only functions that can be continuous? It has to have a what?
A whole.
A hole, perfect. It needs to have a hole. It needs to have a removable discontinuity. So we're going to find out without a calculator, does that function here have a hole? So here's what we're going to do. I want the limit, define the function f of x at x plus, so it becomes continuous at 5. Okay, I want the limit to be continuous at 5. Limit, define the function f of x at 5. Oh yeah, hold on. Oh yeah. Limit as x approaches 5 of the square root of x plus 4 minus 3 over x minus 5. You guys ready? Chavez, I don't understand what you just did, and I don't understand what you're doing, and I don't understand anything that you're writing. Okay. Sorry. Let me explain. Oh, that was a joke, but it wasn't very funny. I apologize. Okay. Oh, man. I'll stop, guys. All right. The reason why I wrote limit here as x approaches 5, if this function has a limit, if I get a limit, that means I have a hole there. Because remember what the whole idea of a limit is that. So if I write the limit as x approaches 5, obviously I'm not defined. I'm obviously not defined. So if I do get a value from this limit expression, that means I have a hole at that value. And Chavez, how do you know you have a hole? Well, because I'm not defined at x equals 5. So if I write the limit of this expression and I get a number, I know that I must have a hole at that y value, at that number that I get. Does that make sense to everyone?
Can you repeat that, please?
Yes. The whole idea, see how I wrote the word limit? The only way that you would have a limit, if it does have a limit, is if you have a hole. See? If you have a hole, you have a limit. Now, if you didn't have a hole, let's say I have a 5 here, and let's say I'm trying to solve for this limit here, and I get something like this. I find out that it's a vertical asymptote. Well, if it's a vertical asymptote, that's it. You don't have a limit. If it's a vertical asymptote, there is nothing you can do to make this continuous. But if I have a limit, see, this has limit at x equals 5. If I have a limit, I know that that y value, whatever that y value is, all I got to do is plug in that hole and I'll be continuous. So I'm just trying to see if I have a hole. Does that make sense, guys? Does that make sense, Godinez?
Yeah, but how do you just fill in the hole?
Oh,
I'm confused.
yeah. We just fill in the hole like this. Whatever that value is. I don't know. What do you want to call this letter? Z. So we just go make f of 5 equal to z, piecewise function, and there it is. You can say this.
You can just do it?
Yeah, you just do a piecewise. Square root of x plus 4 minus 3 over x minus 5, as long as x does not equal 5. And when x does equal 5, make it whatever that letter is.
So you basically make like a horizontal line where the value is always 5.
I wouldn't say horizontal line because we're talking about a point. So if you see this 5z, that's just a point. I'm making a piecewise function and I'm just filling in the hole. All right, let me do this, guys, so you guys can see what I'm talking about. Because until I do, you're going to be just looking at it like, I don't understand. So look, I'm trying to see first if I have a limit. So now that I see this, I'm going to multiply by the conjugate of the numerator, because that's when I want to see if something special happens. From the bottom, nothing's going to happen if I multiply by x plus 5. I'm going to have x squared minus 25, and that's not going to help me. So I'm going to multiply by the conjugate of the numerator. X plus 4 minus 3 over x minus 5 times x plus 4 plus 3 over square root of x plus 4 plus 3. This is the same thing as 1. Anything times 1 is itself. The top is similar to difference of squares. Chavez, what do you mean? That's like a minus 3 is like a plus 3. It's similar to difference of squares. So when I do that, here's what you're going to get. Limit as x approaches 5. And square root times square root, that's just x plus 4. Negative 3 times a positive 3, that is a minus 9. OMG, look at that. Over x minus 5. And I'm not going to bother distributing this because it would be ugly. In the numerator, limit as x approaches 5. In the numerator, 4 minus 9, that is 5. Oh, wait, that's a plus 5. No, that's a minus 5. What's wrong with me? X minus 5 over x minus 5, square root of x plus 4 plus 3. The x minus 5s are going to cancel, guys. And now I have a limit. Oh, that squiggly came out. 1 over 5 plus 4 is 9. Square root of 9 is 3. 3 plus 3 is 6. There it is. That is the y value of the whole. Y value of whole. All right. How do you make it continuous? By stating. Oh,
I'm sorry.
what's up?
How did you go from the numerator being x plus 4 minus 9 to x minus? Oh, JK, never mind. I'm done. I got it.
You're not dumb, Miss. Don't say that. I did difference of squares, so I just spoiled it out. I just distributed.
Yeah, I just missed the simple. We're fine.
It's all good, Miss. It's all good. Math life, Miss. Let's see. What was I going to say? Oh, yeah. Nope. I already forgot what I was going to say.
Wait, I don't get how you got x minus 5 as a numerator.
Oh, I
It's
just
the
did 1 minus 9.
Oh, okay, thanks.
Oh, that's what I was going to say. All right. Here's how you make it continuous, Mazuka. You just say f of 5 equals 1/6.
Yeah, I got that now. So you literally just like add a point. Okay.
Yeah, we just had a point. So here it is. If you want to see it in the piecewise to make it continuous, you would write the function. So square root of x plus 4 minus 3 over x minus 5, as long as x does not equal 5. And then down here, you will put 1/6. So here's my piecewise function when x equals 5. Which is the same thing as saying, what's f of 5? F of 5 is 1/6. We're doing okay, guys?
Yes.
Okay, we're almost done. We're almost done. We got one little theorem to talk about. And it's actually a big one, but it's not hard to understand. The intermediate value theorem. All right, theorem 8. Obviously, I got this from some textbook. I'm not labeling what theorem is what. So by now, we should have covered 8 theorems, I'm assuming, because it says theorem 8. We're not keeping track. The intermediate value theorem. So do me a favor, guys. Read this and tell me if you understand it. And then we'll come back. We'll give you 45 seconds. Do we understand it?
I think so.
What about all y'all? It's okay to say no, guys.
No, I didn't understand it.
Okay.
Yeah, me neither.
So here's what it's saying. It's saying, the intermediate value theorem, that if at a point A you have a y value, and a point B you have another y value that is higher than the other one, then the intermediate value theorem states that you cross every single, I don't like that they go down here, but that's fine, that you cross every single number between f of B and f of A. Chavez, you still don't make sense, and I still don't know what you're talking about. Okay, here's another example. If I tell you f of 3 equals 7, and I tell you f of 5 equals, and I'm telling you that the function is continuous. F is continuous, because that's a big deal. If it's not continuous, we can't do this. And f of 5 is -3. Did this function cross the x-axis between 3 and 5? What do you think, Viacana? So I'm telling
Wait,
you,
could you repeat it?
yeah, I'm going to repeat it right now. If I'm telling you f of 3 is 7, and then I tell you that f of 5 is negative 3, did this function f cross the x-axis between x equals 3 and x equals 5?
Yes,
Yeah, how do you know that?
because it went to the negatives.
Yeah, because there was a sign change, correct? That is intermediate value theorem. Every number between 7 and negative 3 for y, you hit, and you know that when you cross the x-axis, the y value is 0. So that's what the IVT is, that you hit every single number. Does it tell you how many times you crossed? No. You do not know how many times that you crossed the x-axis. All you know is that you definitely crossed it at least one time. That's it. Do you know if this function went all the way to 10? Well, we don't know. Maybe just like here, it went down and then it went up a little bit past f of b. So maybe it did go to 10, but we don't know. It can't be guaranteed by the intermediate value theorem. IVT is the abbreviation, guys. The only thing that the intermediate value theorem guarantees is that I hit every single y value between 7 and negative 3. So for some value c, it definitely was negative 1 on that interval, where c is between 3 and 5. That's a c. And you can pretty much say f of c equals 0, f of c equals 1, f of c equals 2. It definitely guarantees somewhere between 3 and 5 that it was that value somewhere. Does that make sense, guys?
Yes.
If you cross the x-axis on your example one, how come the other one didn't cross the x-axis?
What do you mean? I don't understand.
Well, like you said, you know that it's continuous because it crossed the x-axis and became negative, but the picture doesn't do that.
Oh, well, this is not correlated to that picture. I was just doing something random.
Well, yeah, I know that, but does it have to, sorry, does it have to cross the x-axis to use that theorem?
No, of course not. No. You do not have to cross the x-axis. Here's an everyday example. Wildiness. So you're driving to calculus Saturday session for your first mock exam, which is obviously my calculus class is your favorite class for everyone. Yay, go Cardinals. You look down at your speedometer. It says 55. Did you, at any given moment before the instant you looked at your speedometer, travel exactly 52 miles an hour? What about 59 miles an hour? Okay, so if your speedometer says 55, were you at any moment going 52 miles an hour at some moment?
Yes.
Yes.
Yeah, definitely. The only way you can get to 55 miles per hour is if you cross 52 miles per hour. Now, at any moment, were you traveling 59? Maybe, but the IVT does not guarantee that. The only one that the IVT guarantees is a 52. IVT guarantees 52 mph. IVT does not guarantee 59. It doesn't mean that we didn't hit 59. We just can't guarantee it. The 52 we can because we looked at our speedometer and it said 55. Does that make sense, Godinez?
Yes.
Now, it does not tell us how often we hit 55. It just tells us that we hit 55 for sure at least once. Cool or not cool?
Cool.
Cool. All right, so look at this. Without a calculator, it says, can the IVT be used to show that there is a solution for the equation f of x equals 0? It doesn't have to be 0. I could have any number there. But in this case, they're being nice and they just want to know if you cross the x-axis or not. All right. Without a calculator, we're just going to see what f of 1 is. So we plug in a 1. This is my interval, by the way. That's how they say interval. Well, it says that there, interval. Sorry, guys. I'm not insulting your intelligence. I apologize. 3 times 1 cubed minus 5 times 1 squared plus 1 minus 3. Let's see what that is. 3 minus 5 plus 1 minus 3. 3 minus 5 is negative 2. Plus 1 is negative 1. Minus 3 is negative 4. So I see negative 4. So I'm going to see what f of 2 is. If f of 2 is a positive number, then it's going to be yes. If f of 2 is another negative number, then it's going to say, we're going to say we don't know. Or we're going to say IVT cannot be used because we don't know if it did cross or not with what we know here. 3 times 2 cubed minus 5 times 2 squared plus 2 minus 3. All right. 2 cubed, 2 times 2, 4, 4 times 2 is 8. 8 times 3, 8, 16, 24. Minus 2 squared is 4. 4 times 5 is 20. Plus 2 minus 3. All right, let's see what that is. 24 minus 20 is 4. 4 plus 2 is 6. 6 minus 3 is 3. Okay. F of 1 is negative 4. F of 2 is 3. Can I use IVT on this one to prove that f of x is 0?
Yes.
Yes. Yes. IVT can be used to state f of x equals 0 somewhere for, and then I would give my x values, somewhere for, you don't have to put the equal sign, but I already did, somewhere between 1 and 2. Since, and I guess I should write, since f of 1 equals negative 4 and f of 2 equals 3, maybe put a semicolon, sign change occurs between x equals 1 and 2. Let me put that over here. Sign change occurs between x equals 1 and x equals 2. There we go. I said it with beautiful language of math. You can probably say it in less words if you're like super good at writing essays and all that good stuff. If you're really good at transferring information. And there it is, guys. Let's all come back.